This is the first video of this week 2. We're looking at immunity. I've removed the slides in the lymphatic system, so it's just immunity from your Tortora textbook, chapter 22. So there's two types of immunity. One is called specific immunity, and the other is called non-specific immunity. The non-specific is also called innate immunity. It's because it's innate to us. We all have this type of immunity naturally. When we think of pathogens as invaders to our body, the best way to avoid an infection by a pathogen is just to keep them out. So if we keep the outside out and the inside in, we tend to be healthier. So the first line of defense is the barrier between the inside and outside, that's skin and mucous membranes. So there's a physical barrier and there's a chemical barrier provided by these things. So the physical barrier is a barrier that just physically keeps things out. So that would be the epidermis itself, the continuity of the cells of the epidermis and the mucous membrane. There are other projections off of those cells, things like hairs in the nose that will trap foreign things. Mucus, so snot basically, traps microbes and doesn't even let it come into contact with the mucosa. There are cilia on a lot of the mucosa, especially the respiratory tract, that move things away from you. So that's all part of this defense. There are various fluids that provide physical, mucus being one, but tears are another, saliva, urine, vaginal secretions are involved, as is vomiting and defecation, I guess. All of these things really prevent the microbes from getting into you. So if you ingest food that has pathogens in it, you're going to feel nauseated and you're going to vomit and therefore not let them invade your body. You're going to get them away from your body. Now there's also various chemicals that are secreted by the skin and the mucous membranes that act as a chemical barrier. This is not a barrier against chemicals, but chemicals that are secreted that act as a barrier against pathogens. So that would be things like the oil glands in the skin, the sebaceous glands. They're acidic secretions because bacteria just don't live very well in acids. That's why we use vinegar to pickle cucumbers and things. Like, they will stay not rotted for quite some time because of the acidity. Sweat, stomach secretions, vaginal secretions, they're all acidic, so they all manage to keep out pathogens. They make it inhospitable to pathogens, let's put it that way. The second line of defense comes into play when the first line is broached, when the pathogens actually get across the barrier and get into us. And so these would be considered internal. Now, we still maintain the first line of defense to keep further invasion, but once something gets into us through a cut or through whatever, we have this second line of defense. And basically the second line of defense can be broken up into three categories: stuff, like substances as it were, processes, things that our body does, and cells that are involved in the non-specific immunity. So we're going to look at the antimicrobial substances first. So basically this is stuff that the body produces within the body that um, help you uh, in defense against pathogens. So the first one is interferon. Now, when viruses invade our body, they can't reproduce on their own. So what they do is they go into cells, they invade cells, and they take over their protein synthesis things, the translation and transcription, and they hijack it, and basically these infected cells make copies of the virus, and that's how viruses reproduce. So once that cell is invaded by the virus, there's nothing it can do except make viruses. It uh, and that's not good for the body. So what that cell does is when something is wrong with that cell, it releases uh, a substance called interferon. And what interferon does is it moves into the cells that are surrounding that cell in the tissue, and it basically shuts down the protein synthesis. It shuts down translation and transcription, and therefore makes those surrounding cells useless for the reproducing virus. So it doesn't kill viruses. It just makes the the tissue cells useless to that virus. Now, unfortunately, it makes the tissue cells useless to the tissue as well because they're not making the proteins they need to make. Um, but the whole idea behind interferon is to slow down the spread of the virus, because if it's reproducing more slowly, then it's not going to infect as many cells. It's not going to spread throughout the body as quickly. It only works with viruses. Now, when there are cellular pathogens coming into you, things like bacteria, then what happens is they don't enter cells; they stay in the interstitial fluid. And we have these chemicals called complement, and what complement does is it actually injects proteins into the lipid bilayer, the cell membrane, the plasma membrane of the microbe. And it does three things. It causes cytolysis, so basically it pokes a hole in the microbe, and the intracellular fluid flows out. So basically you're stabbing the microbe. It also promotes phagocytosis. It allows macrophages to eat that microbe. Not only has the microbe been wounded and is probably slower, but it gives the complement proteins give a handle to grab hold of, for the macrophage to grab hold of. My favorite analogy to this is if you picture the macrophage as being a bouncer in a bar, big, slow, lumbering bouncer, but very strong. And what he does before he punches you is he grabs your shirt so that you can't get away. Complement is the shirt. By this protein becoming part of the cell membrane of the microbe, it provides a grab hold for the macrophage, or the neutrophil for that matter, and makes it so that the microbe can't get away while it's being phagocytized. The third thing that complement does is it releases inflammatory chemicals. So it's the start of the inflammatory reaction, which is a very important reaction. It's very very necessary to fight infections and to prepare for healing. There are also proteins that are released that are called iron binding proteins. And basically, what they do is they make iron unavailable for the bacteria, and then the bacteria can't get the oxygen they need, and because there's not enough iron to carry the oxygen, and it inhibits the reproduction, the growth and reproduction of the bacteria. So it slows it down, makes it easier for the macrophages to deal with them. The last one is one called antimicrobial proteins, AMPs. They basically are involved with the killing of microbes. They do all kinds of different things. There's all kinds of different ones, but basically they're involved in chemotaxis. They're involved with attracting the cells that participate in the immune response to the spot where the microbes are. The cells that are involved, there's two types of cells. So the first four were substances. The next two here are cellular. So these are living cells that our body produces. The first one that we'll talk about is the natural killer cells. Natural killer cells kind of patrol the body, and they are looking for any cell that is not correct. Every cell in our body puts out a marker on its cell membrane called major histocompatibility complexes, MHCs. And what they do, they act like a uniform on a soldier. They say that I belong here, I belong on this side. Natural killer cells are looking for cells that are somehow not right. So fundamentally, these are cells that are invaded by viruses, so they're infected, or they are somehow abnormal, like they're dysplastic, so the beginning of cancer, that kind of thing. So as that cell that's infected by a virus is releasing its interferon, it's also putting viral proteins in its major histocompatibility complex and making the MHC appear wrong compared to the other body cells. So what the natural killer cell does is when it sees that, it just kills that cell. So it kills our own body cells that have a problem. And it does it by releasing a protein called perforin, which makes perforations in the cell. It just basically dissolves it. It releases granules of enzymes that also induce cell death, apoptosis. Now, even though they kill the cells, they haven't killed the virus in the cell. The only thing that will actually kill the virus are the phagocytes, and these are neutrophils and macrophages. They come to the area and then they basically engulf the microbe, whether it be a bacteria targeted by complement or a virus released by the natural killer cells into the interstitial fluid. Now, something to note about phagocytes is that they will only work in the interstitial space. They don't invade into cells. What we have to do is get the virus out of the cells. So the natural killer cells are like the SWAT team that kick down the door and throw the tear gas into the house that the bad guys are hiding in. The phagocytes are like the cops in the street that get the bad guys when they run out of the house, the hideout, as it were. So the phagocytes eat the pathogens. You all know about phagocytosis, I'm sure. There's endocytosis, but really what happens is uh, the the phagocytes get ingested, uh, or I'm sorry, the microbes get ingested by the phagocyte. This step one, chemotaxis, is the phagocyte is called to the area of infection. Number two is adherence. The phagocyte, the macrophage, adheres to the microbe, and that's where complement comes in, right here. Then the pseudopods grow around it, ingest it here, and then there are enzymes in vacuoles inside the cell. They're called lysosomes that come onto the vacuole that has the microbe, release the digestive enzymes. They kill it and digest it. We reuse the proteins, the amino acids that are in the microbe, and anything that's indigestible becomes a residual body within the phagocyte. So those are the two types of cells: natural killer cells that get microbes out of infected cells and into the interstitial fluid, and the phagocytes that actually do the killing of the microbes. The processes involved are really important. One of the most important ones is inflammation. Now, in modern medicine, inflammation has gotten a bad reputation, but without inflammation, we would be very loath to heal. It says here that it's a non-specific defensive response of the body to any sort of tissue damage. So you get inflamed even when there's mechanical damage. And it's saying there are 4 signs and symptoms. Well, some authors say 4, and most authors say 5. Now, the CMTO has decided that it likes 5, and there's a mnemonic for it. It's PRISH, PRISH, and it stands for pain, redness, immobility, swelling, and heat. So add immobility to this here. And really what it is it's a way of limiting the spread of the microbes by keeping them in one place and preparing the site for tissue repair. If there's damage done to the drywall in your house, you have a party and somebody breaks the drywall, you can't just fill it up with drywall compound. What you have to do is cut out all the damaged drywall back to good drywall and put a new piece in, and you make a better repair. People that do body work on cars don't just fill rust holes. They cut the metal, or they cut the door or whatever back to good metal, and then they make the repair from good metal. It's the same thing. If we have damaged tissue, we don't want to make the repair from the damaged tissue. We want to make repair from good tissue. So we have to dispose of damaged tissue to prepare the stage. So 3 stages of it. At first, what we have is something called vasodilation. And so when vasodilation happens, it brings more blood to the area. And the more blood means it goes red. The blood's hotter, so it's heat. The extra fluid creates the swelling. The swelling creates the immobility. And the stretching of the tissues creates the pain. So that's the cardinal signs of the PRISH. And it's all around vasodilation. And so the inflammatory chemicals are really vasodilators, like histamine, for instance. And when the blood vessels vasodilate, they become more permeable. So more liquid gets to leave them uh, and go into the interstitial fluid. But with that liquid also goes the white blood cells that are involved in fighting the infection, and we call that emigration. It used to be called diapedesis, and you will see that term every now and then. And then after the fight has happened, then the tissue starts to repair. So the increased diameter of arterioles, more blood flows, brings more supplies and removes the debris. The increased permeability, stuff that's normally retained in the blood, pass out. The chemicals involved really are histamine, kinins, which release things, prostaglandins that are involved in pain. And one of the things to note is that the nonsteroidal anti-inflammatories tend to fight against prostaglandins. Advil is stops the production of prostaglandins, and that's why it's a painkiller as well as an anti-inflammatory. When the blood vessel here dilates, then what happens is the phagocytes can leave the bloodstream and fight the microbes at the site of injury, or dispose of the dead tissue cells, the ones that the remains that the natural killer cells have left behind, and we call that emigration or diapedesis. Chemotaxis is chemicals that call those phagocytes to the area, and then emigration is how they get out into the interstitial fluid. Neutrophils are the most predominant. We have the most of them, and so they're the first ones on the scene. They die off fairly quickly. Monocytes come to the scene, and then they become macrophages once they're in the interstitial fluid. They're much better at phagocytosis than the neutrophils. Pus is some amalgamation of dead phagocytes, damaged tissue, dead microbes, all of that stuff becomes pus. So what is inflammation? It's a response to tissue damage or the threat of invasion, triggered by physical trauma, invasion with foreign bodies, hormonal change, autoimmune activity, which would be tissue damage anyways. It protects us from invasion. It limits the range of the contamination. By swelling, stuff doesn't get out into the rest of your body and prepares the area for healing. At first you get vasoconstriction, but then you get vasodilation. It's one of the reasons that we put ice on something, on an injury that's getting inflamed, that has acute inflammation, because ice causes vasoconstriction, so it fights the vasodilation, and you don't get the symptoms of, you don't get the prish. We're not going to worry about that slide. Or that one. I'm not worried about the types of cells that are involved. I said that the chemical mediators coordinate this cellular activity, so that would be like the prostaglandins and that kind of stuff. Let's just drop down to here. There's the pain, heat, redness, swelling, loss of function or immobilization. When I was in school, we learned dolor, calor, rubor, tubor. whatever. Okay, the last of the processes is fever. Now, fever is a hugely important thing. What it does is it raises the metabolic rate to allow you to fight disease better. So it's an abnormally high body temperature. It's usually from some sort of infection, but other types of tissue damage can do it. So there are various chemicals that are released when when a fever starts, and we'll call them all pyrogens. Generates pyro, so heat producers. So the interleukins and the cytokines and all of that collectively are known as the pyrogens. Fever protects the body from infection. It raises heart rate. It increases the distribution of white blood cells. It limits iron, so bacteria don't grow as well. It speeds up chemical reactions. All of those things are important things for fighting infections. It doesn't really become a problem until we get over 40 degrees. You don't want to bring it down too fast as well. Now, probably one of the things that my wife and I fought about with the kids was that she always wanted to break the fever when I thought too soon. I would rather see people be a little more symptomatic, a little sicker for a shorter period of time, because fever helps you fight it. So within reason, you should keep the fever going. So fundamentally, then, that's it for the non-specific. This has been a fairly quick overview of it, but the first line of defenses is keeping the outside out and the inside in through the mucous membranes and the skin. The protective barriers are physical barriers, and there's chemicals released by those barriers that act to help as well. If microbes get into your body, then we come at it three ways: with substances that are produced by the body, which would be interferon, complement, antimicrobial proteins, and the iron binding proteins; by cells that aid in the fight, so living cells made by the body that aid in the fight. So that would be the phagocytes, neutrophils and macrophages being the most important one, eosinophils to a lesser extent, and the natural killer cells, which are a form of lymphocyte that kill our tissue cells that have a problem with them. The last thing are processes that the body does to set the stage to make these other things work better. So inflammation to limit the spread of problems, facilitate the fight, and to set the stage for healing, and fever to speed up the body's reactions and slow down the microbes.